The following video reports on an experiment conducted into the durability and manufacturing time of bone and antler projectiles. In prehistory, both bone and antler presented themselves as suitably hard, workable materials for constructing the tips of hand-thrown weapons. However, as Necht states, evidence from the archaeological record suggests a clear preference for antler over bone in Stone Age projectile assemblages. Some of the sites providing evidence for this trend are listed here. Each of these sites featured a large assemblage of organic projectiles, the majority of which were constructed from antler. Each site also featured a large number of bone implements, so this seems to have been an intentional choice and not due to any shortage in bone. In an interesting study, Tejero 2012 analyzes the data for El Castillo, Ischwitz, and La Quina, and finds that bone was in fact liberally used to construct domestic implements such as awls, while projectiles were restricted to being made of antler only. What's more, there is evidence that this antler was intentionally collected for the purposes of projectile construction specifically. While bone is a natural byproduct of eating, and therefore readily available to any hunter-gatherer group, antler is only present on mature males of certain species of deer, and, as Avabo 2000 states, only sufficiently mineralized during a brief 2-month period of the year. Furthermore, the presence of shed antler bases at sites such as El Castillo, mentioned before, shows that the inhabitants undertook intentional collection of discarded antlers. This activity was separate from food gathering, suggesting that antler was a highly valued resource in its own right. So why this enthusiasm for antler projectiles? Necht suggests that antler is a more durable raw material than bone, producing projectiles that survive more impacts. Krauss et al. Rationalized this with a materials study that shows that the fibrous nanostructure of antler renders it far stronger under inelastic deformation, protecting it from catastrophic failure. However, this increased durability is also likely to decrease the workability of antler compared to the more brittle bone. Given this, and the fact that bone was more readily available from other activities, a question of optimality is raised here. Optimality is an important factor in ancient technology studies, and is discussed at length by archaeologists such as Ugenbright and Rogers. Essentially, a tool that is more difficult to obtain or produce must pay for itself by performing more efficiently at its function. This concept will form the basis of this experiment's hypothesis. It is hypothesized that antler projectiles will take longer to produce than bone projectiles, but will also be more durable. In this way, the performance of antler projectiles will outweigh the cost of their production, resulting in a more optimal tool than bone. A 2-part investigation was used to test this hypothesis. The first phase was to construct the projectile points. The antler points were constructed using the double groove and splinter technique. This approach was selected based on Pétion and Ducasse's assertion that this technique was the dominant method of antler working from 28,000 BP onwards. The technique involved the use of red deer antler, stone burins, and sandstone grinders. Following newcomer's procedure, the antler was soaked for 7 days prior to working to increase its pliability. Using the burins, 2 parallel longitudinal grooves were carved into the surface of the antler. Carving continued until the grooves penetrated to the spongy interior. Following much trial and error, this tongue of antler was eventually levered out. The tip was then ground to a point with a sandstone. This same procedure was subsequently carried out on bone. Despite newcomers' claim that soaking has no effect on bone workability, the bone was also soaked for the same duration that the antler was. This was done to minimize the number of uncontrolled variables between the 2 projectile types. However, one important consideration for this study is that numerous sources would dispute the use of the groove and splinter technique on bone. Several sites found that most bone projectiles show signs they were splintered off by direct percussion, perhaps coming out as byproducts of the marrow extraction process, and then were only minimally retouched afterwards. For this reason, another sample of bone projectiles was created by directly striking a bone, then grinding the sharper splinters using sandstone. Since it required so little effort, this procedure was applied to both cooked and raw bone to slightly increase the scope of the study. In sum, 4 types of projectile were produced. Due to the long duration of the groove and splinter method, the first 2 types were represented by only 3 replicates. Meanwhile, 10 replicates were created for the much quicker splintering technique. The next phase of the investigation was to test the point's durability. In their use context, the points would have been launched horizontally. However, without specialized launching apparatus, the force of impact achieved by this method is very difficult to control. To reduce the variability between each throw, this investigation instead used a vertical trajectory, passively dropping the points directly downwards from a controlled height. Each therefore experienced an identical acceleration due to gravity of 9.81 meters per second, as well as being attached to a controlled weight of 420 grams. As such, each encountered the ground with a force of 4.12 newtons. The weight was added to ensure the points did eventually break upon encountering the ground, and was achieved by hafting the points securely to a heavy cricket stump using duct tape. However, it should be noted that the weight chosen was arbitrary. Future investigations could alter this to produce a force that better reflects that achieved by different methods of human-driven throwing, or alternatively, experiment with more historically accurate methods of hafting. In this small investigation, however, the points were simply dropped with as many variables controlled as possible, and a tally was kept of the number of impacts experienced until an irreparable breakage occurred. These are some examples of the breakages observed on the projectiles. Different breakage types were observed between the two materials. Bone projectiles seemed to shatter catastrophically after only a few impacts. By contrast, antler points broke far more gradually. As the number of impacts increased, these points seemed first to gradually bend and eventually split transversely along that bend. Furthermore, it is unquestionable that antler points were the more durable projectile. On average, it took 182 impacts to observe a breakage in antler. Groove and splintered bone lasted an average of only 5.7 impacts, slightly longer than the splintered bone averages of 2.8 and 3 impacts for cooked and raw bone respectively. The two techniques also exhibited starkly different manufacturing times. A percussion splintered bone could be produced in under 5 minutes, regardless of whether the bone was cooked or raw. By contrast, the groove and splinter technique for antler took an average of 131 minutes. Interestingly, however, this production time was not significantly decreased for groove and splintered bone. In fact, a p-test shows no evidence of a significant difference between the two materials' production time. Perhaps this suggests that the soaking process negates any differences between the workability of antler and bone. When production time is plotted against durability, the stark differences between the two datasets become clear. Splintered bone points consistently show a very short production time and low durability. By contrast, groove-splintered projectiles require far greater production times. However, in antler this is noticeably offset by a much greater durability, in keeping with the hypothesis of this investigation. So, on balance, which projectile type is the most efficient? This optimality graph provides an indication of the payoff between the two variables. Here, a higher gradient represents a more ideal tool, that is, one with a lower production time in relation to its higher durability. Here, the highest gradient of 1.39 is indeed exhibited by antler tools. This suggests that the costs of these tools' greater production time is outweighed by the benefit of their higher durability. That is, in terms of durability, they are a more efficient investment than our bone tools. Hence, the hypothesis of this investigation has been supported. Percussion splinter bone tools are somewhat less efficient, with gradients of approximately 8.5, while double groove splinter bones are significantly less so. That is to say, despite the fact that double groove bone was slightly more durable than percussion splintered bone, this small benefit was heavily outweighed by the cost of its production. In other words, making a bone projectile with the double groove splinter technique is not worth the effort. These trends may help to explain some of the archaeological observations made by the studies discussed earlier. Specifically, they suggest that the inhabitants of these sites were gearing their toolkits towards greater durability. These hunters were willing to invest significant time and energy in the preparation of antler projectiles in order to produce a tool that survived more impacts. By contrast, bone, especially highly worked bone, was avoided as a raw material for projectile production, because even despite its cheaper production time, the weakness of its tools made them less optimal overall. Finally, it is important to mention a number of limitations of this study. For one thing, the sample size of 3 is very small, and more replicates of the double groove splinter technique would be necessary to draw conclusions with stronger confidence. Furthermore, there are a number of factors of projectile technology that were beyond the scope of this investigation, but if included, may have impacted the results. For example, as Tejero, Christensen and Bodu assert, antler-working techniques other than the double groove splinter technique are available, and these may confer very different production times. Had these been used, the optimality data obtained may have been very different. Finally, and perhaps most significantly, the experimental setup of dropping a projectile vertically onto a concrete surface does not emulate the nature of real-life projectile flight. This procedure was conducted purely to ensure a situation of controlled variables in this very small-scale experiment. Improving on these limitations should be the focus of any future, more well-resourced studies on this topic.